You cannot escape knowledge. Science is knowledge.
It's an interesting time to be talking about my father.
He was very open-minded and willing to consider all sorts of ideas. Much more important to him to have new ideas than, to be sure that they were right from the beginning.
We are not doing science just because we want to earn Nobel Prizes. We're doing it because we want to understand the secrets of nature.
But very often when he was working, he was determined to get the right answer. He'd say, well, yes, but never mind. I said, but how do you know, you see? And he would lean back like this and twirl his moustache.
Physicists that are more mathematically minded. There are others who are very phenomenological. Salam was certainly a combination.
This story begins in Jiang, in Punjab, also called the Land of the Five Rivers. Punjab boasts a long, rich cultural tradition, thanks to the coexistence, albeit at times forced, of the two main Indian cultures, Hindu and Muslim. Time follows the rhythm of a ferry which crosses the river, and the animated life of market days. Here, on January the 29th, 1926, Abdus Salam was born. His family was of Muslim origin and had lived in Punjab for many generations. His father came from the ancient Indian clan of Rajiptus and belonged to the Hamadi, a Muslim minority sect which in the course of the years had often been persecuted.
His father was pre-sensitized by a series of very vivid dreams which told him exactly what his son was going to do and that his son would go on to change the world.
My grandfather again one day dreamt of this young boy climbing high up into the tree. And it was his son who was climbing very, very high into the tree. And after a while, my grandfather couldn't see the boy anymore. He'd gone so high into the trees. And he shouted up to him to be careful. And of course, the little boy, being a very brave little boy, shouted back down, "Don't worry, grandfather, I'm absolutely fine."
And going up and until he vanished in the sky. So that also, as he interpreted at that time, that he will achieve heights in the lifetime.
When he was 14 years old, Abdus Salam became a local hero. He won a scholarship for the government college in Lahore, having attained the highest marks ever registered in Punjab.
Whenever he was going on a bicycle to school or college, and the shopkeepers came out and clapped and said, "Oh, this is the boy who stood first." And his name became so famous in few days, everybody, "Oh, this is the Muslim boy. First Muslim boy," he said. How did he do it?
His father's greatest ambition was for Abdus Salam to join the Indian Civil Service, that is to say, a national organization set up by the intellectual elite of the British Empire, which required passing an extremely difficult examination. In order to apply, however, the candidate had to have studied in Great Britain, a condition which, Salam, was fulfilled thanks to a number of very lucky circumstances, the last of which was a telegram from Cambridge's St. John's College.
St. John's College, Cambridge, had a tradition of taking students from the Indian subcontinent. They had one in 1946 who was going to do English literature. He dropped out at the last minute, and Salam's application conveniently slotted in. He had a place at St John's College, Cambridge.
At the beginning of September 1946, Abdus Salam boarded a ship leaving Bombay and headed for England. 3 weeks later, he arrived in Liverpool, where he stood on the dock with his trunk of books beside him. The morning after, young Salam left for Cambridge, greatly charmed by the green English landscape. Cambridge is one of the oldest and most prestigious universities in the world. For over 700 years, it has been synonymous with a world of culture and knowledge. Fields and woods line the River Cam, which crosses the city, on whose banks you can find beautiful medieval and neo-Gothic buildings, home to the Cambridge's famous colleges. Cambridge is a truly sacred place for studies in physics. It has a long, glorious tradition built up over the course of the centuries, especially in the field of the theoretical unification of all physical phenomena. The first to carve out this path was Isaac Newton, Lucasian professor at Trinity College. His laws of motion, combined with universal gravitation, bridged the gap between terrestrial and celestial dynamics.
Newton, in some sense, was the first, but there were many others that followed. The highlights, perhaps, are Maxwell. Maxwell, of course, extremely famous for many things, but most notably the unification of electricity and magnetism in his famous equations.
Cambridge also hosts the Cavendish Laboratory in Abbey Lane Street, where in 1897 J.J. Thomson discovered the electron and gave birth to the physics of elementary particles. In the early 1920s, it became the leading laboratory for nuclear physics under the direction of Ernst Rutherford, the scientist who was the first to discover the nuclear structure of the atom. And it was again at Cavendish, at the beginning of the 1930s, that James Chadwick demonstrated the existence of neutron.
Abdus Salam is at Cambridge studying mathematics to get into the Indian civil service. Up until that time, Salam had been led by suggestions from his father. While he was at Cambridge, a very strong influence came when he heard for the first time lectures by a famous physicist, Paul Dirac.
He was Lucasian professor starting, I think, when he was 28 years old, so he became professor at a very young age, following his extraordinary work on combining special relativity with quantum mechanics and the Dirac equation, which led immediately to his prediction of the existence of antiparticles. And somehow that was the beginning of particle theory, and in particular with quantum field theory, which is the tool that was used to understand theoretical particle physics.
Salam heard lectures from Paul Dirac, and he realized that mathematics was not an abstract subject in its own right, but it was something that could be used to understand the world about us, and thereby to understand more how God, Allah, worked his wonders.
In only 2 years, Abdus Salam passed his mathematics tripos, and following the suggestion of his tutor, the astrophysicist Fred Hoyle, he spent his 3rd year studying for the physics tripos. Experimental physics is a necessary path of studies, as pointed out by Hoyle, who told him, if you want to become a physicist, even a theoretical one, you must do the experimental course at the Cavendish Laboratory. Otherwise, you will never be able to look an experimental physicist in the eye. Although Salam was at Cavendish Laboratory, the old instruments of Rutherford's laboratory were not so easily tamed. The art of experimental physics was not his, and so he amused himself by inventing new theories to justify the data that he couldn't account for. But, thanks to his brilliant qualities as a theoretical physicist, in only 1 year, Salam was able to succeed in a very tough challenge where other great talents had failed. He secured a first-class physics tripos. At St. John's College, he spent countless hours in the extremely well-stocked library, reading all the scientific classics and strolling in the cool gardens at the back full of roses, so utterly different from the heat and the dust of his own country. The sweet flow of a river calm accompanied his hours of study. In 1949, Salam's scholarship in England came to an end, and he had to go back to his homeland. As he returned home, he discovered that as consequence of the fall of the British Empire, the Indian continent was undergoing great changes, which would lead to the birth of the two independent countries, India and Pakistan. He stayed in Jiang just 6 weeks, time enough to get married, and with a new scholarship in his pocket, which barely guaranteed his own sustenance, Salam left once again for Cambridge. He had finally decided to become a theoretical physicist. Abdus Salam was very attracted to the quantum field theory, a theory that constitutes the base for all the processes involving elementary particles, where particles may be destroyed and their energy used to create other particles, in a never-ending dance of creation and annihilation, as brilliantly described by Richard Feynman's graphical formalism.
We can describe the phenomena of light in this way, that an electron on the sun, when it has just the right energy and momentum, can emit a photon, and that photon, or light particle, travels through space and comes into our eye, where it shakes an electron in the eye and we see it. This can be represented in a diagram, which we can represent the electron in the sun moving and emitting a photon, which is absorbed by the electron in the eye. In the micro world, at very high energy and very short distances, we find that the interaction of two charged particles is exactly the same kind of a thing and can be represented by the same diagram. The only difference is that this photon doesn't have to have exactly the right energy and momentum. We can borrow energy for a while and give it back. The result of this interchange is to produce a force between the two particles, the electric force, as a matter of fact, or a magnetic force, which holds the electrons, for instance, around the nucleus in an atom.
Salam would have liked to work with Dirac, whom he considered the greatest scientist of the 20th century, but Dirac was well known for not accepting any students. He therefore turned to Paul Matthews, who suggested him to analyze some divergent expressions, apparently meaningless, obtained by applying Feynman's formalism to more complex processes.
You can't do those calculations. Why not? Well, they tell you that the effects, which was thought to be very small, the extra effects due to other particles sitting in our way, so to speak, those effects will become infinitely big. So it's not a small effect at all. Those effects would not only start to dominate over the previous calculations, they would ruin the whole theory.
Physicists had to handle this delicate issue for a long time, up until the end of the 1940s, when Julian Schwinger, Richard Feynman, Shinichiro Tomonaga, and then Freeman Dyson showed how this difficulty could be cleverly overcome. Thanks to a technique called renormalization, it was possible to tame all those ill-famed infinities of quantum electrodynamics. And it was with the very problem of renormalization that in 1950, at just 24 years old, Salam made his entrance on the stage of international physics by placing the last missing piece of a puzzle. This would later become the subject of his PhD thesis and the key to his international reputation among theoretical physicists.
As a graduate student, I had spent a lot of time reading Salam's papers. There had been a decade earlier, a great advance in understanding the way to do calculations involving photons and electrons, the theory so-called quantum electrodynamics. And Freeman Dyson, had given a general formulation of how to deal with the infinities that keep coming up in these calculations. And his treatment was not complete. And Salam was the one who had completed Dyson's analysis.
The theoretical physicists of Cambridge had also been enthusiastic about the spectacular success of a renormalization theory. The excitement surrounding this creative effort kindled in Salam a passion for research, which throughout his life was to remain one of his most distinctive features. Salam went to Princeton to work with Paul Matthews, and there he had the chance to meet Robert Oppenheimer and other leading figures in the physics of those years, including Eugene Wigner and John von Neumann. He also often met Albert Einstein, who used to stroll in the fields, completely lost, as always, in his thoughts. He came to know Richard Feynman closely during one of his seminars too.
And I started to speak and invoked Feynman. This was the greatest surprise of my life to see him in the audience. And I started by saying, take an elementary particle and give it a quantum field. And his very first question was, what is an elementary particle? And I had a great difficulty in answering that question. He wanted to know whether a man could have a field associated with him, quantum field associated with him. Was a man an elementary object or not? And in the end, I had to silence him by simply saying, Feynman, if you know the answers to the questions you are asking, why don't you come and give the seminar?
The experience in Cambridge and in Princeton was inspiring and exciting. It was equally exciting to go back to Pakistan thanks to an offer from the University of Lahore. The year was 1951, and Salam was very pleased of the idea to the students of his country everything he had learned in the years abroad. However, it soon became clear that reality was bitterly different.
Abdus Salam wanted to teach people quantum mechanics, relativity, and what was happening in modern physics. The people at Government College Lahore were still steeped in 19th century physics, and they did not understand or appreciate what Abdus Salam was trying to teach.
Problem was, they did not respect him. They gave him the most junior job in Government College Lahore.
Abdus Salam had never been a sportsman. The most sporting thing he'd ever done was either ride on his father's bicycle or move a chess man on a board. Despite this, the principal of Government College Lahore suggested to Salam that he become the coach of the college soccer team. But I don't think that soccer team was a great success.
He just said to my father, our father, Daddy, I have come here. I am a research student. I went to Cambridge to study and propagate knowledge everywhere. Now I'm here now. These people don't know anything. They don't care about me. They don't respect me. Students don't pay attention to me. I'm wasting my time here. What I'm doing here? What should I do?
The few journeys to Cambridge and the meetings with Paul Matthews relieved his frustration in part, though at the same time nourishing his feelings of anguish on each return to Pakistan. In 1952, during one of these visits, Salam had the opportunity to speak with Rudolf Peierls about Enrico Fermi's theory of beta radioactive decay, according to which a neutron decays into a proton, an electron, and an antineutrino. Speaking about the neutrino, a particle whose existence had been suggested by Pauli in the early 1930s, Peierls asked Salam a crucial question. The photon mass is zero because of Maxwell's principle of a gauge symmetry for electromagnetism. Tell me, why is the neutrino mass zero? This question, which neither Peierls nor Salam knew the answer to, became one of Salam's greatest intellectual challenges in explaining the mysterious world of the physics of elementary particles. But there were more pressing problems. In February 1953, Pakistan was ravaged by a civil war of a religious nature, and the sect of Ahmadi, to which Salam belonged, was the main target.
Abdus Salam learnt that his life was threatened, and he and his family had to hide in a safe house to safeguard their own livelihood. How could he continue with his research under such conditions? Not only did he not know what research needed to be done, not only did he not have any research partners anymore, but his life was physically in danger.
In 1952, Abdus Salam left Lahore for good and returned to Cambridge. In Cambridge, after years of isolation, Salam went back to intense work and surrounded himself with a team of top experts, including young John Polkinghorne.
Salam arrived, a young man, full of enthusiasm, full of ideas, very much in touch with the frontiers of things in particle physics. So it was very inspiring and encouraging and exciting to make contact with him.
Meanwhile, particle physics was making incredible progress thanks to the study of cosmic rays and the construction of increasingly powerful accelerators.
The accelerators were speeding up particles like electrons and protons, almost the speed of light, smashing them into targets of material, producing new particles from the energy. E equals mc squared, energy turning into stuff. And they started discovering lots and lots of particles. So many that they ran out of letters of the alphabet to describe them. But this then raised the question, how are all these things related to each other? Can they all be fundamental?
Of nature's most fundamental interactions, the most mysterious may be weak interaction. It is capable of changing the identity of particles and of provoking their decay. Understanding its mechanism took long years of research, starting from the end of the 19th century after the discovery of the first radioactive decay thanks to the efforts of Henri Becquerel and especially the research of Pierre and Marie Curie. Wolfgang Pauli, in order to explain the beta decay of a neutron, was the first physicist who postulated the existence of a neutral and massless particle, the neutrino. Such a particle fully characterizes the weak interactions. Neutrinos are produced in great quantities during the course of nuclear processes that take place within the Sun and other stars. The existence of this elusive particle was experimentally proven only in 1956 by Frederick Rines and Clyde L. Cowan, who for this reason were awarded a Nobel Prize.
The neutrino, almost no mass at all, no electric charge, flies through space without caring about anything. Why it's there, who knows?
As you know, weak interactions were, or rather, beta decay was found at the turn of this last century. And at that time, it was a great puzzle. How could the electrons come from inside the nucleus? Nucleus was supposed to contain protons and neutrons and maybe a little bit of light emitted, but nothing else. But nevertheless, beta particles came, they were identified as electrons.
The first step towards understanding these processes was taken by Enrico Fermi in 1933, with his theory of beta decay.
La teoria di Fermi spiega la radioattività beta dei nuclei, ma poi si scopre, dopo la guerra, che altre particelle subiscono lo stesso tipo di decadimento, quindi la particella mu e poi successivamente le particelle strane e così via. Fermi aveva un'idea, cioè che la radioattività beta dovesse essere spiegata in maniera analoga all'elettromagnetismo. Questa idea motivava più o meno la sua teoria e 23 anni dopo Feynman e Gell-Mann e Marshak e Sudarshan scoprono che è così.
How can parity be violated? Parity is the fact that left and right are the same. That you look at a coordinate system which is right-handed and look at left-handed, you will say, well, they are the same.
Every particle had its mirror image, and it functions just as its mirror image. But then when you look more carefully, you find that there's something odd. Something didn't quite work. the way you might have expected. And the more you came in touch with the weak interactions, the more you realize there's something crazy going on with this mirror symmetry. Not quite right. And the extreme example of this is the neutrino. Neutrinos are these notoriously inert particles. They don't interact with anything at first approximation. They only interact very, very sporadically with other forms of matter. When they do, you discover something very startling. Neutrinos are very different from their mirror image. In fact, it was Cecilia Yardscock who once gave a talk comparing neutrinos with vampires. They don't see themselves in a mirror. If you look at the mirror, you don't see nothing. There is no mirror image of the neutrino.
At the end of the 1950s, it became clear that the laws of physics are not the same when they are looked through a mirror. There is indeed a violation of the symmetry under reflection. Two young American physicists, Tsundao Lee and Chenning Yang, underlined that there was no experimental evidence confirming the validity of right-left symmetry in weak interactions. Lee and Yang described these results during an international physics conference held in Seattle between the 17th and the 21st of September 1956. Salam attended the conference, and on the plane home, he couldn't stop thinking about what he had learned. He kept reflecting on why nature should violate left-right symmetry in weak interactions. Just before landing, he understood the answer, that nature had the choice of a left-right symmetry violating theory, with a neutrino which traverses exactly with the velocity of light spinning only in one direction.
When Salam arrived in England, he wrote down the consequences of this proposal, and everything seemed to be pointing the right way. But Salam was unsure that such an unconventional idea was worthwhile. He sent it to Wolfgang Pauli, who people acknowledged as the Chief Justice of Physics. Pauli said, "My son, do not worry me with this rubbish. Go and think of something better."
But this time, Pauli was wrong. At a press conference on January the 15th, 1957, Madame Wu announced that an experiment with a nucleus of cobalt-60 had demonstrated without doubt that God is left-handed. It was a major shock for physicists to discover that weak interactions violate right-left symmetry, as Salam had thought. And it was bitterly ironic for him to discover that in the same year, Yang and Lee received the Nobel Prize for their penetrating investigation of the so-called parity laws, which led to important discoveries regarding elementary particles. In the words of a Pakistani writer, Hanif Qureishi, London is like a 5,000-room house. The game is to find out how the rooms are laid out and to manage to visit them all. The capital of a former British Empire was the next step in Abdus Salam's life. In 1956, Patrick Blackett, Nobel Prize for Physics in 1948 and director of the London Imperial College, met Salam and offered him a chair in his institution. Salam enthusiastically accepted his offer, and in January 1957 moved to London to become professor in applied mathematics. Salam was joined by Paul Matthews, and together they were able to give birth to one of the most brilliant and dynamic teams for research in theoretical physics. Tom Kibble was part of this young group.
Salam was an extremely vibrant, lively individual and enormously inventive. He was a very stimulating person to be around. He had huge numbers of ideas about possible theoretical developments. Some of them crazy, some of them turned out to be extremely fruitful.
Salam's career bloomed. He became a member of various academies, and in 1959, at the age of only 33, he entered the prestigious Royal Society. At the Imperial College, he was also assigned the chair of theoretical physics, which was specifically created for him. During his inaugural lecture, Salam examined the situation of the research in physics of the elementary particles and the problems which were still open. He underlined that his generation had been extremely lucky to be able to face such an outstanding challenge in the research for an internal harmony and a deep, pervading symmetry of the laws of nature. In Salam's opinion, symmetry should be the key to understand the embarrassing proliferation of elementary particles in strong interactions. These particles are collectively known as mesons and hadrons.
There seem to be new particles emerging every few weeks from the experimenters. And people began to feel that there could not be so many elementary particles. One had to bring some sort of order into this. And that's triggered a search for symmetries.
Symmetry plays a very special role in physics. But in a sense, we learned in the last century that it plays a fundamental role. It really underlies. We learn to understand the basic forces of nature.
What is symmetry? Symmetry really means that you see a phenomenon here, you see the same phenomenon there. So symmetry in general is compare two different phenomena in nature and discover that they are described by the same laws.
If I take an object like this, there is a symmetry. When I turn it around, it looks exactly the same no matter which way I turn it. That notion that there are relationships between apparently different objects is something which has proved of great importance in particle physics.
The idea of symmetry in physics is, of course, much older than Salam. But as far as particle physics is concerned, that's the domain of speciality of Abdus Salam, and he was definitely one of the first few who saw the relevance of symmetry in particle physics.
All physicists are interested in symmetry, but Salam was particularly so, and this may be just because of his cultural background. I think he was always very much aware, and he has said so himself, that the universe for him was a reflection of a great God creating it all, and he wanted to understand the equations that were written in the notebooks, if you like.
At the beginning of the 1960s, more than 100 particles had been discovered. The question for theoretical physicists was, could these many different particles be all elementary? Or rather, to quote Salam, are some of these particles more elementary than others?
People were motivated to look for patterns and global symmetries, to see whether the multitude of elementary particles that were being discovered in the particle accelerators that were built after the war exhibited any kind of patterns that suggested an underlying global symmetry. And they emerged.
In this period, Salam suggested to a PhD student of his, the Israeli Yuval Ne'eman, to further explore the symmetry of strong interactions, thus generalizing an idea originally elaborated by Werner Heisenberg, who had assumed that the proton and the neutron are basically different conditions of the same entity, the nucleon. Thanks to Salam's encouragement, Ne'eman discovered that besides the proton and the neutron, there are other heavy particles that could be classified following the principles of symmetry, and that these particles are naturally organized in families. The same structure, called SU3, was independently discovered by Murray Gell-Mann from the California Institute of Technology. Following these symmetry principles elaborated by Gell-Mann and Neyman, it was finally possible to classify the particles of strong interactions and to actually foresee the existence and the mass of a new baryonic particle, omega-, which was triumphantly discovered at Berkeley in 1964. All this marks the beginning of a quark theory. The application of the symmetry principles started to show all its force as a powerful guide for discovering nature's laws. Trieste is a border city, located at the most northern point of the Adriatic Sea. The poet Umberto Saba described it thus: Trieste has an awkward grace. If you like it, it is like a bitter, voracious youth, with blue eyes and hands too large to give flowers, like jealous love. 1960, and it was not long since Trieste had been given back to Italy. The years of the war and the occupation, first by Tito and then by the Allies, deeply marked the city. A border city, the last outpost of the Western Front. A city of 1,000 souls, harsh as the karst rock, beautiful as its sea, ever seeking its identity. The traces of its glorious past as the main harbour of the Habsburg Empire were still very evident, and its jewel is still today the castle of Miramare. It was June, and in the garden house of a park, also known as the Castelletto, a group of physicists were saying the last goodbyes after 2 days of animated discussion. The meeting had been organized by the young director of the Physics Institute of Trieste, Paolo Budinic, who for years had been working on getting Trieste into the worldwide network of research in order to give the city a future.
Se si guarda una fotografia storica che è appesa nei corridoi del centro, si vede un giovane fisico con i baffi e senza barba, che era Abdus Salam.
E fu un incontro molto, molto interessante, perché fu basato su discussioni scientifiche, però abbiamo avuto tutti l'impressione che abbiamo messo una prima pietra, forse una prima zolla, forse più che una prima pietra, ma indubbiamente c'è stato qualche cosa che è stato un momento di inizio, questo è stato indubbiamente.
Abdus Salam è venuto e ha tenuto la sua lezione sulle simmetrie in quel periodo e è stato subito incastrato da Paolo Budinic, il quale aveva quest'idea di fare qualcosa a Trieste, ma anche Salam voleva fare qualcosa.
That meeting in June 1960 between Paolo Budinic and Abdus Salam at Miramare's Castelletto marked a turning point in the life of both men. It was the beginning of an extraordinary adventure in the international scene of physics and politics. An adventure marked by obstacles, certainly no easy path. The idea of creating a center where scientists from throughout the world could freely gather seemed crazy, revolutionary, an idea that undermined the heavy international atmosphere of reciprocal suspicion characteristic of the years of the Cold War. The two participated in innumerable meetings at which they showed great ability at piecing together a very difficult jigsaw puzzle. In June 1963, in Vienna, at a decisive meeting of the International Atomic Energy Agency, Salam gave one of the most eloquent speeches of his whole life, and thanks to the support of all the poorest countries in the world, he was able to outdo all the great powers hostile to the idea. It was David's victory over Goliath. The International Center for Theoretical Physics finally became a reality. Trieste suddenly occupied a space in the geography of the international world of science. A small city, and yet a great window on the world. The International Center for Theoretical Physics was first located in Piazza Oberdan, a series of bare rooms which were immediately animated by discussions on symmetry, particles, and issues concerning fundamental interactions.
La piazza Obodan quella volta non era la sede provvisoria, ottenuta anche con miracoli, perché la storia di questo centro è un susseguirsi di miracoli.
E io ricordo Salam nel corridoio urlare un giorno: devo riempire questo maledetto posto. I have to fill this bloody place.
Piazza Oberdan was a temporary location. Indeed, Paolo Budinic was able to gain considerable local support, and Prince Raimondo of Turn and Taxis gave him a plot of land near the castle of Miramare, where on the 18th of June 1964, the first stone of the International Center for Theoretical Physics was laid. The center was inaugurated in June 1968, when Abdus Salam and Paolo Budinic finally made their dream come true. Abdus Salam was the first director.
ICTP, of course, is a unique institution in the world, and this has been created by Salam, of course with the help of a lot of other good people like Budinic and many others. But Salam was its creator and driving force behind it. His personality, his passion, his compassion to help other people, to deprived people in developing countries. This was radiating from him, and it was not artificial. You could see that the man believed in it. At least I could see it. I was, on many occasions, I witnessed the way that he sees, he feels it. He traveled a lot. Even in those days that he could hardly walk, he would go to remotest corners of the world to propagate science, to talk to politicians in developing countries, in poor countries, try to awaken them to the importance of science in modern world.
There are 3 or 4 things that are special about Salam. I want to say what they are. The first one is that although he talked about development and the value of science for development all the time, and that was one of his passions, he really also knew that he had to do good science himself. And without himself being a good scientist, he knew there was nothing he could really give to the rest of the world.
Era una persona delle qualità straordinarie. Forse la cosa che colpisce di più era la sua capacità di cambiare in tempi brevissimi dal fare scienza al fare amministrazione.
Era tipico di Salam che se uno si avvicinava a lui era sempre pericoloso, perché lui avrebbe trovato rapidamente qualcosa da fare alla persona. Ed effettivamente appena ha saputo che io lavoravo su altri temi mi ha detto: ah, questo è importante, dovevi andare a parlare con la gente, con tutti gli scienziati di qui del centro e dirgli l'importanza di fare più di una tematica, perché lui era convinto che si dovevano fare almeno 2 temi in fisica. Uno, quello di scienza basica, scienza fondamentale che veniva pubblicato, un altro qualcosa più rilevante per la società.
Salam was actually a very, very remarkable, very unusual man. I only realized a bit later that he had a very complicated personality, actually, and he had this habit of displaying certain aspects of it to certain people.
Salam era, come ho sottolineato, molto interessato alla scienza e alla scienza di punta, però aveva una concezione della scienza molto molto più vasta e soprattutto la vedeva come il tipico campo in cui c'è una possibilità di dialogo tra tutte le genti, quindi ha trasformato questo suo interesse e il suo impegno scientifico anche in un impegno che aveva dei risvolti politici diretti, soprattutto dal punto di vista della fratellanza umana, della possibilità di comunicazione tra etnie, religioni, ideologie diverse.
Salam wanted to help the scientists, not only just the physicists and the mathematicians, but the scientists, and that's why he considers himself not an island, but somebody who really serves humanity, and especially the developing world people and the scientists there.
I was really admiring him enormously, because that really encouraged me to really do more in science and to do for science in developing countries.
Salam for me has been one of my great scientific heroes. I always followed his physics when I was a student, and I always admired him because of that. But for me, the most important part is that he, at the same time that he was able to do top science, he was also able to start and run this institute, which is ICTP, to promote science in developing countries. I met him when I just finished my PhD. We had long discussions, and coming also from a developing country myself, we shared the vision of the importance of science for developing countries. And at the moment when I got to be selected to be the director of ICTP, for me it was very emotional, because that gave me an opportunity to continue Salam's mission to help to keep his dream alive.
Salam's life started to be frenetic, back and forth between Trieste and London, where he still held his chair at the Imperial College. And it is in London that in 1968 Abdus Salam married Louise Johnson, a molecular biophysicist with whom they later had 2 children. His research developed enormously, thanks to extremely fruitful collaborations, among which the ones with Bob Del Burgo and Chris Isham, and especially with John Strathday, with whom he developed the theory of supersymmetry. Another notable collaboration was with Yogesh Pati, with whom Abdus Salam proposed the famous model of particle physics which predicts, among other results, also the decay of a proton.
There was a tradition in Trieste that following a seminar there will be a tea gathering, more or less once a week. Now, in one of these tea conversations, I casually mentioned to Salam that the electric charge must be quantized. Just like the hypercharge arbitrariness should be removed, electric charge should be quantized. And in that context, one should understand why is it that the electron and the proton have exactly equal but opposite charges. So this is something very basic, electron and proton charge being exactly equal and opposite. And to understand it, I suggested to Salam that quarks and leptons must be members of one multiplet. When Salam heard it, I was quite surprised. Instead of showing reservations about the idea, he immediately said that sounds like a very good idea. Let us develop it together.
Since its inception, the ICTP has welcomed an endless stream of scientists from all over the world, including many who have been awarded the Nobel Prize or who have proceeded to win the prestigious prize, as for instance Paul Dirac, who liked to spend the summer there to discuss physics with Abdus Salam, or Sheldon Glashow and Yoichiro Nambu, major actors of the theoretical scene, or Carlo Rubbia, a leading figure of experimental physics. However, despite all the efforts of Abdus Salam and Paolo Budinic, the early years of the centre were not easy, in particular with regard to the uncertainty of funding which jeopardized hard-gained results. Fear of closure was a regular nightmare. But 1979 marked a turning point. The most crucial moments in the development of physics are those characterized by great synthesis. That is, when the common origin of different phenomena is discovered, as with the genial insights of Newton, Maxwell, and Einstein.
Then in the 1950s, the idea began to develop that radioactivity and electromagnetic radiation, like light, are actually 2 manifestations of the same thing. Deep down, they are the same, but in the world around us, they look very different. The rainbow of lights and radioactivity of rocks look very different to us, but deep down, perhaps they're the same.
In the 1960s, scientists were starting to believe that electromagnetic and weak interactions could be described by means of the same theory, by using the gauge theory formally introduced by Chen-Ning Yang and Robert Mills.
So you have to understand a little bit how the Yang-Mills theory was constructed. What Young and Mills had observed that a central feature of Maxwell's theory, the old theory of the 19th century, was a concept called gauge invariance, which really meant that you have some freedom in describing the fields. And at every point in space and time, again, you have some freedom in writing your equations. Symmetry was beautiful, but at the same time caused all sorts of problems. The Young-Mills particles would interact with themselves directly and the other particles. The symmetry made this theory much more complicated. The equations looked more complicated. And, well, there were also new problems on the horizon that people didn't have yet so much experience with.
Finding a gauge theory capable of unifying weak and electromagnetic interactions was one of Salam's most ambitious projects. Following an original idea of Julian Schwinger, Abdus Salam had made his first attempts in this direction already in 1958, together with his old co-worker John Ward. Since the photon is responsible for electromagnetic interactions, argued Salam and Ward, there must exist the two new particles, W plus and W minus, responsible for weak interactions, and they must be on the same footing of a photon.
So for the electromagnetic force, the photon has got no mass and the theory works beautifully. For the weak force, the W boson, the analogue of the photon, has a big mass, and that is a big problem. You get infinity instead of numbers that are sensible. How do you solve that?
In this theoretical scheme, there also was a problem regarding parity, since the photon respects this symmetry, whereas W particles should violate it. The theory was therefore still far from satisfactory. In order to solve these problems, Salam made use of the key concept of spontaneous symmetry breaking.
The secret of nature is symmetry, but the texture of nature arises from symmetry breaking.
We're all very much aware of symmetry, the idea that things have patterns, are very pleasing to look at. And I suppose the Taj Mahal is a perfect example of symmetry. You look at it from the front and you see an exact mirror image. What happens on the left happens on the right, exactly so. But most things aren't symmetric. All the things around here, the shapes and patterns, no obvious symmetry in them at all. The building over here is a nice example. It is not symmetric. There is a tower on one side, but not on the other. And the moment you see something that is not symmetric, you want to know why.
There are in nature systems which are perfectly symmetric, although the most stable state is asymmetric. A good example is a pencil balanced on its point, a clear case of a rotational symmetry system. But the symmetry isn't stable. The pencil will eventually fall in a casual direction, and if one observes the final situation, one can hardly imagine the existence of the initial symmetry under rotation. Theoretical physicists pose the following question. Could there exist some sort of symmetry between the photon and the W particles which would spontaneously break so as to generate the observed mass difference and at the same time to violate the parity conservation?
Why weren't the relations among them exact? Why did it seem that you had a fundamental principle of nature, a symmetry property, which was only approximate? Very puzzling.
Ironically, it had actually been Abdus Salam who, together with Stephen Weinberg and Jeffrey Goldstone, had further complicated the matter. In 1962, in fact, they showed that a spontaneous breaking of global symmetry necessarily implies the existence of particles with no mass, a result highly undesirable since these particles have never been observed in any experiment.
When Goldstone, Salam, and I wrote our paper, we regarded the result as very negative, very disappointing. And so I put into the preprint of the paper a little quote from King Lear. The idea of I should explain, the idea of spontaneous symmetry breaking is that although the equations have the symmetry, the vacuum state, which is a solution of the equations, does not have the symmetry. So the quote from King Lear was, "Nothing will come of nothing. Nothing will come out of the vacuum that we're interested in. Speak again."
The great breakthrough was to get mass into the equations without spoiling all of the nice, beautiful things that had worked for quantum electrodynamics. And the trick had been discovered by at least 6 people. I'll give all their names. Higgs, Brout and Engler in Belgium, Guralnik, Hagen and Kibble in England, within the space of a few weeks in 1964, all independent of each other, had the same insight. It is possible to break symmetry and create mass.
If the symmetry is not like the kind of symmetry that groups the proton and neutron together, but is more like the symmetry that governs electromagnetism, so-called gauge symmetry, the kind of symmetry that Yang and Mills were thinking about as a generalization of electromagnetism to the strong forces. If the symmetry was that kind of symmetry, then when it was spontaneously broken, you would not get massless Goldstone bosons. You would also not get massless particles like the photon, but all of the photon-like particles associated with the broken symmetries would get a mass.
Using the results of Sheldon Glashow, who had identified the correct group of symmetry SU2 cross U1, in 1967, Steven Weinberg and Abdus Salam demonstrated that it is possible to generate the right masses of the intermediate bosons, leaving, however, the photon massless. They also predicted the existence of a new intermediate boson, Z0, responsible for those processes in which there is no exchange of electrical charge between the particles which participate in the phenomenon. For this unified theory, Salam coined the term electroweak theory, a term which was immediately taken up in scientific language. But the work of Salam and Weinberg was ignored for several years, also because their theory did not seem to be renormalizable, that is, a victim of a terrible infinities of quantum corrections. However, 2 important events completely changed the scenario. The first took place in the theoretical field, the second in the experimental field. From a theoretical perspective, in 1971, Gerard demonstrated how to renormalize the theory of Weinberg and Salam, thereby freeing it of the infinite corrections of Feynman's graphs. This fundamental theoretical step forward convinced physicists to reconsider the electroweak theory with greater attention, and moreover, to work out the consequences coming from the neutral currents, which enable particles to collide with other particles without any exchange of electrical charge in the process. From an experimental perspective, on the other hand, in 1973 there was the first confirmation of the existence of neutral currents and an estimate of the masses of the particles W and Z thanks to the huge Gargamel bubble chamber at the CERN protosynchrotron facility.
There's something like that in the feeling that those equations are really about the real world, and that using those equations one can predict what will come out of an experiment. I can't explain how marvelous that is.
When I speak of these distances of 10 to the minus 13 centimeters, short-range forces, long-range forces, and so forth, to me as a physicist, these are irrelevant. My task, if you like, is to go behind the reality of these short-range and long-range forces and to see the unity which exists between them.
Thus, the standard model of elementary particles was officially born.
The standard model, which was essentially completed by 72 or something, 73 after QCD, it was a fantastic progress, which is hard to explain now to people who had not known this situation before. Because all of a sudden we had a theory, we had rules, we could compute, and we could compare with experiments.
The standard model is a mathematically consistent theory both of electroweak and strong interactions. It is the model which enables us to predict all the properties of matter, from astronomic to subatomic scales. Given these successes, the Royal Swedish Academy of Sciences set in motion the process which led to the announcement of a Nobel Prize in 1979, shared by Abdus Salam, Sheldon Glashow, and Steven Weinberg.
Because when you get the Nobel Prize, you're warned in advance that it's happening. But apparently there's a sort of final phone call that confirms it. And as it happens, by pure chance, I was actually in Salam's office when this phone call came, you see. And so he picks up the phone. I suppose someone says, OK, you've got the Nobel Prize. Put it down again, and he looked at me with a huge beam on his face. He leaned back in his chair. One of the gestures he always did is he leant back in his chair and he would twirl his moustache, looking at me with a big beam. Chris, he said, the same old tricks, they work over and over again.
I'm happy to say he shared the Nobel Prize in 1979. And we were all together, of course, in Stockholm. I must say Salam had one great advantage over Glashow and myself, because we had to get into white tie and tails, which is the classic costume for getting the Nobel Prize. And although I like getting into a dinner jacket, often called a tuxedo, I find white tie and tails an extremely clumsy outfit, and I try to avoid it as much as possible. And Salam wore what I think the Swedes call native costume, and a jacket and loose pants, very Pakistani looking, and slippers with curls bottoms. And he looked gorgeous. And but not only did he look better than Glashow or me, he was much more comfortable. So that's right, he wore a turban also. So he was the one you looked at when you looked at the stage. But I forgive him.
Nobel Prize, 1979. I was quite young. It was important to him that he wear the nachkan and the turban. He was, after all, the first Muslim to win the Nobel Prize, first Pakistani. Since him, how many Muslims have there been? Amit Suwail, not many. So tying the turban was not something that he did on a regular basis as a boy. He would have done it daily, I expect, but he hadn't been doing that for 50 years. So, we had provided the best turban we could find, but nobody knew how to tie it, or nobody knew, rather, how to tie it to a standard that would satisfy him. But we did it again and again and again and again until it was done.